This is what you get when you put 1.0 in binary. There's 7 ones here. 7! And it gets weirder because there's another 1 hiding. How do we get 8 ones out of 1.0? Let's unravel this mystery by learning how floating point numbers work. So you probably expected a 1 in binary to look like a 1. Kinda obvious, right? Now let's start adding to it, counting up by 1. Simple enough, right? For integers, this is exactly how it works inside the computer. But what if I want to add this much, or this much, or this much? The simple representation here won't work. So what's the most efficient way to put numbers like these into 32 bits? The solution is what we call a floating point number. The actual point is here, if you're wondering. Formally, these are IEEE 754 32-bit numbers, but you don't need to remember that. We'll call them floats for short. Let's explore how these work by comparing two numbers, our initial 1.0 and 4.5. Here's 4.5 as a float. What's the same and what's different between these two? The first bit's the same. If you've studied binary integers, you might know what this first bit does. It's the sign bit. 0 for positive, 1 for negative. So that's one bit we understand. Only 31 more to go. Sounds like a lot, but it's only 2 pieces to understand. Let's focus on the 4.5. We'll get back to 1.0 after we understand each part. These 8 bits are the exponent. We like binary or base 2 in computers, so the exponent goes on a base of 2. Now 4.5 is awfully close to 4. What number here will get us to 4? That's right, it's 2. So we might expect a 2 in our exponent. But this binary is equal to 129? Let's just subtract off 127. And now we've got 2. Problem solved. Okay, but that's ridiculous. That can't actually be how it works. It is how it works. See, 127 is what we call the bias. Here it is in binary. We subtract this bias off to get the actual exponent. 10 here, which is 2. Nice, right? But we're not done yet. Let's look at these 23 bits. So most of these bits are 0. What's this guy? Remember that we have a point right here. Everything after this is some part of a whole number. That is, it's a fraction smaller than 1, so we call it a fractional part. You'll see other terms for this part if you check other sources. They'll call this part the significand or mantissa. Yeah, the guys who invented this stuff liked weird words. Anyway, in a binary number, after the point, we go to negative powers of 2. What would 0.5 or 1/2 be as a negative power of 2? It would be 2 to the negative first, which would look like this in binary. But that's not what we have. We've got 2 to the negative third, a number you might be more familiar with as 1/8. So we want 1/2, but we have 1/8. To see how we go between them, look at the big picture again. We multiply these. 4 times 1/8 will give us 1/2. And this, in essence, is how floating point numbers work. We take our exponent, subtract off the bias, and raise 2 to that power. Then we multiply that by the fractional part and get... Not the number we were looking for. Where'd the 4 go? We forgot the hidden 1. Remember that from the start of the video? When we add the hidden 1, the math works out. So we act like there's a 1 here, but if you look at the binary in your computer for 4.5, you won't find a 1 in that spot. Why did the engineers who created IEEE 754 floats hide a 1 here? Efficiency. To see why the hidden 1 is an efficient choice, let's look at how we might write 4.5 as a binary number times a power of 2. This is what we just saw, but wouldn't this also be equal to 4.5? Or this, or plenty of others? Here's the thing, we only get 32 bits. That'll give us around 4 billion possible numbers. A lot, but not endless. Aren't we wasting some of those possibilities if we can use more than one combination to represent a single decimal number? Yeah, we are. We stop the waste by requiring a single one to be right before the point. Now, for any given decimal, there's only one available representation. And if there's always a 1 here, do we need to use up a bit to store it? We don't. That also frees up an extra bit to use. So that's how the hidden 1 makes floats more efficient. So we're back to the starting question, but now we know what the parts are. If you want to remember how floating point numbers work later, pause now and try to remember what each colored section does. We've got the sign bit here, 0 for positive, and then the exponent. This binary is equal to 127. What else was equal to 127? The bias. You see where this is going. We subtract off the bias and get 0 for our exponent. And what's any number raised to the 0 power? Right, it's 1. And here's the fractional part, also called the significand or the... these two parts multiply together. The fractional part looks like all zeros, so we might expect 0. But we have that 1 hiding here. We do the multiplication and get 1.0. Now you know the basics of how floating point numbers work. Want to go deeper? That's awesome. Watch this other video now and you will be one step ahead. Thank you.